Back to the latest lecture or pre-lecture for Physics 150. And as I threatened a little while ago, I want to discuss in some detail Gauss's law for certain situations. The first situation being a cylindrical distribution of charge. And the thing is, we're not going to make it a bunch of point charges all along a line. This cylinder, we will consider the actual volume. We'll consider inside the cylinder, and we'll consider outside the cylinder. But the one way in which we will simplify this problem is that we'll restrict ourselves to the center part of the cylinder. As you move away from the center part of the cylinder, edge effects can make the issue pretty complicated. But we can make some really good predictions about the mid part of the cylinder, and these predictions are pretty good when you are close to the cylinder. So we are going to look at the whole cylinder. We're going to approximate it as uniform, and it'll give us a very good representation of what's happening very close to the cylinder. We'll assume that the cylinder contains a charge Q, a total charge Q, but that this is distributed uniformly throughout the entire volume of the cylinder itself. Now, this would not happen if this cylinder were made of conducting material. If the cylinder is made of conducting material, the charge accumulates on the outside, the outer surface of the cylinder. But since it's made of insulating material, we can place charge uniformly throughout the entire volume, and it will stay there. Charges do not move through an insulating material. If we look at it in cross-section, the light blue circle represents the actual cylinder, the actual cylindrical distribution of charge seen from edge on. And it has a radius of capital R, physical radius of capital R. But in order to use Gauss's law, we need to imagine a couple of imaginary volumes. One imaginary volume will allow us to determine what's going on the inside of the cylinder, and the other imaginary volume will allow us to determine what's going on outside of the enclosed cylinder. Of course, our imaginary volume reflects the symmetry of the situation. We have a cylindrical distribution, so we are going to imagine a cylindrical shape. That happens to be centered along the central axis of the actual cylinder. One of these imaginary cylinders is represented by the red dashed circle. That's really the cross-section of a three-dimensional cylindrical distribution. And the surface of this imaginary cylinder, within the surface, within the volume of this imaginary cylinder, lies the entire volume and the entire charge of the actual cylinder. One of the important things that you need to determine in using Gauss's law is how much charge is enclosed within the volume of your imaginary cylinder. In the case of the red one, the entire charge is enclosed. So Q enclosed, Q subscript enclosed, is equal to Q, the entire charge of the cylinder. But it's different for the imaginary cylinder represented by the blue dashed circle. If you look at the figure, you'll see that the blue dashed circle has a radius that is less than the radius of the actual cylinder. That means that this imaginary blue cylinder does not encompass the entire charge. It only encompasses a fraction of the charge. But we can use some geometric ratios to determine the fraction of charge that is enclosed. And the fraction of charge that is enclosed is based on the volume of our imaginary cylinder divided by the volume of the actual cylinder. Because of the uniform distribution of charge, the ratio of the cylinder's volumes is going to be equal to the ratio of the charges enclosed by the imaginary cylinder compared to the actual cylinder. So if you look on the left-hand side, you'll see this expression, pi times little r squared times capital L over pi times big R squared times capital L. Well, the volume of a cylinder is the cross-sectional area, pi r squared, times the entire length of the cylinder, which I'm saying is capital L. So pi times little r squared times L is the volume of the imaginary cylinder. Pi times big R squared times L is the volume of the actual cylinder. And the charge enclosed in the imaginary cylinder depends upon that ratio. In that ratio, there's a factor of pi in the numerator and a factor of pi in the denominator. And there's a factor of L in the numerator and a factor of L in the denominator. Those cancel out. We are left with little r squared over capital R squared. And so the enclosed charge within the imaginary blue volume is little r squared over capital R squared times the total charge of the cylinder. So we need to determine an expression for the enclosed charge in order to apply Gauss's law. So we've done that for the red cylinder that encompasses the entire volume of the actual charge distribution, and the imaginary blue cylinder that encompasses only a fraction of the volume of the actual cylinder. The other part of Gauss's law that we have to worry about is an expression for the electric flux. If you'll recall, Gauss's law says that the electric flux is equal to the enclosed charge divided by epsilon naught. We've come up with an expression for the enclosed charge on the right-hand side of the equation. We need to come up with an expression for the electric flux on the left side of the equation. And this is why we choose a shape that is symmetric with respect to the actual charge distribution. Our actual charge distribution is cylindrically symmetric, so we will select an imaginary shape that is cylindrical. And by doing that, it makes the expression for the flux not so bad. In this determination, we're going to ignore edge effects. And by ignoring edge effects, the only area that we are going to worry about is the area of the barrel, the side of the cylinder. Not either end piece, but just the area of the side. And it turns out that the surface area of the side of the cylinder is equal to the circumference times the length, 2 pi r times L. And because we've chosen our imaginary shapes to be symmetric with respect to the charge distribution, it turns out that the electric flux is simply equal to this surface area times E. Now, the goal of the problem is to come up with an expression for E, so we don't have anything for it yet. We're trying to solve for it, but I can say that the electric flux for this cylinder is equal to the surface area of the cylinder, 2 pi RL, times E. So now we have an expression for both sides of Gauss's law. Now, one of these expressions applies to inside the cylinder, and the other expression applies to outside the cylinder. But in both cases, the electric flux is 2 pi RLE. Notice that's a little r. We're talking about the radius of the imaginary surface when we determine the flux through that imaginary surface. Another way of writing Gauss's law, instead of saying Q enclosed over epsilon naught, we could say that the electric flux is equal to 4 pi K times Q enclosed. In either case, whether we're talking about outside the cylinder or inside the cylinder, the expression for the electric flux is 2 pi times little r times L times E. And if we are talking about outside the cylinder, the enclosed charge is all of the charge, Q. And so if we are outside the cylinder, we now have an expression for the strength of the electric field. It's 2 times K times Q over R times L. We also can determine it for inside the cylinder. This takes just a little bit more algebra, but not just a cancellation, really. On the left-hand side, 2 pi times little r times L times E. Same expression for the electric flux. It's equal to 4 times pi times K times the enclosed charge, which we said earlier was the total charge times little r squared over capital R squared. We now want to solve to come up with an expression for the electric field strength, capital E. We play around with the algebra, and what we get is an expression for the electric field. It is equal to 2 times K times Q times little r over capital R squared times L. We see that when we are within the cylinder and as we are moving away from the center, the electric field increases. It increases linearly with our distance from the central axis. But once we reach the surface of the cylinder, and as we move further away from the cylinder itself, the electric field strength that we sense drops off. Well, the farther away you are from a charge, the weaker the electric field. And the same thing holds true in the case of this charged cylinder. What might be interesting, though, is that when you're dealing with a point charge, remember that the expression for the electric field of a point charge is KQ over R squared. The electric field strength for a point charge drops off as 1 over R squared, whereas the electric field strength for this long cylindrical distribution of charge simply drops off as 1 over R. So it drops off more slowly. The other situation that I want to look at in this pre-lecture is Gauss's law for a thin conducting sheet. We're going to say that this thin conducting sheet has a total area of capital A, and once again we're going to ignore edge effects, which can complicate the matter. What we want is to imagine charge on only one side of this sheet. This is the situation like between the plates of a parallel plate capacitor. In a parallel plate capacitor, the negatively charged plate, the negative charges collect on one side of the sheet. The positive charges in the positively charged plate collect on one side of the sheet. They don't distribute on both sides of the sheet. So we have a whole lot of charges on the top face of this sheet. We have a little bit of thickness, not much, but a little bit of thickness. And then on the bottom face, we're going to pretend there's no charge. Because this is a conducting sheet, the charge is strictly on the surface. It is not distributed throughout the volume. In this circumstance, we are going to use a rectangular solid. And just to make the math less painful, we're going to say that 2 of the dimensions of this rectangular solid are the same. We don't have to, but it really doesn't matter. So we'll say that this rectangular solid, the top face that is parallel to the actual sheet of charge has dimensions of x by x. The dimensions of the bottom face would also be x by x. Notice that the top face and the bottom face of our imaginary volume are parallel to the plane of charge themselves. And notice that the 4 sides of our imaginary rectangular solid are perpendicular to the sheet of charge itself. That perpendicularity is important because when I have to calculate the electric flux, recall, electric flux goes as E times A times cosine theta, where theta is the angle between the direction of the electric field and the direction of the area vector. And recall about the area vector that is directed perpendicularly to the plane of the area itself. So if I look at the 4 sides of this rectangular solid, the front side, the left side, the right side, and the back side, the electric field is pointing straight up. And the area vector is pointing straight to the side. For instance, on the right side, the area vector points directly to the right. On the left side, the area vector for that face points to the left. To the front, it points towards the front. For the back face, it points towards the back. Each of those 4 area vectors is perpendicular to the direction of the electric field, which means that theta is 90 degrees and the cosine of 90 is 0. So there is no flux through the 4 side faces of this rectangular solid. There's also no flux through the bottom face because, remember, we don't have any charges on the bottom. We only have charges on the top side. And therefore, the electric field lines simply point upwards from this sheet. And I have some electric field strength E, which I'm going to try and determine, and it passes through this area of the top face that measures x by x. The area is therefore x squared, and the electric flux through that top face is E times x squared. And because the area through each of the, electric flux through each of the other sides is 0, I can say that the total electric flux through this imaginary volume is E times x squared. What about the enclosed charge? Let's pretend that the sheet itself, the entire sheet, has a total charge of Q. Well, the amount of charge enclosed within the imaginary volume is proportional to the area of the sheet inside the imaginary volume divided by the total area. So once again, we have a ratio. The enclosed charge to the total charge is equal to the enclosed area divided by the total area, and therefore the enclosed charge equals x squared over the entire area times the entire charge Q. We now have both sides of Gauss's law. So the electric flux is equal to the enclosed charge over epsilon naught. We said that the electric flux is E times x squared. The enclosed charge is Q times x squared over A. So I have EX squared equals QX squared over A epsilon naught. And the x squareds cancel out. And I'm left with an expression for the strength of the electric field E equals Q over A epsilon naught. We see that the electric field is actually uniform in this approximation. Now, it is unfortunate but true that if you look in physics textbooks, you'll see symbols introduced that they simplify the way the equation is written, but they might make it a little bit more challenging to understand. Two symbols that are frequently used are lowercase Greek letter sigma and lowercase Greek letter lambda. Greek letter sigma is defined to be the charge per area, total charge divided by total area. Lambda is defined to be total charge per length, so total charge divided by total length. Sigma is sometimes referred to as the area density of charge, and lambda is sometimes referred to as the linear density of charge. If we use those symbols, it simplifies the expressions that we've developed on the previous slides. We use lambda for the cylindrical distribution and sigma for the sheet, and we get these expressions for the electric field. For the cylinder, E, when we are inside the cylinder, when little r is less than capital R, it's equal to 2k lambda over r squared, and then that times little r. Whereas if we are outside of the cylinder, then the strength of the electric field is 2k lambda divided by little r. Our expression for the conducting sheet, we can either write it as 4 pi k times sigma, or we can write it as sigma over epsilon naught. Those are interchangeable with each other. Let's take a look at this example. We have a long wire, 2.9 meters long. It's carrying electric current, and maybe at any given instant in time, the amount of charge is 7.82 nanocoulombs. And we want to know the electric field strength 1.35 centimeters away from the wire. Now, for electrical engineers, stuff like this is an important thing to take into consideration, because you have to be careful about the electric field of one wire creating changes in the current in a nearby wire, and you have to take steps to mitigate against that. Let's look at the electric field strength We are told the charge is 7.82 times 10 to the negative 9 coulombs, and that the length is 2.90 meters. And we are 0.0135 meters away from the wire. We're assuming a thin wire. We are beyond the range of the wire. 1.35 centimeters is thicker than just about any wire you're going to see. So it's safe to assume that we are looking at the electric field at a location outside of the wire itself. So we're assuming little r is bigger than capital R. And our expression for the electric field is that it's equal to 2kq over little r times L. We plug in our numbers, and we get an electric field strength of 3,590 volts per meter. You can also record that as 3,590 newtons per coulomb. Let's also look at an example involving a sheet of charge. We have a metal sheet. Knowing that it's metal means that it's made of conducting material. This sheet measures 17.2 centimeters by 15.5 centimeters. And we're going to place charge on it. We're going to replace charge on it enough charge on it to satisfy the following conditions. When we go from a location of 0.515 millimeters away from the surface to a location of 0.725 millimeters away from the surface, we want there to be a change of 1.59 volts. So we're being told what the potential difference is over a particular change in displacement. And that gives us information about the strength of the electric field. You might recall from an earlier lecture that in the case especially of the uniform electric field, that the strength of the uniform electric field is equal to the change in voltage over the change in displacement. Well, very close to this sheet of charge, the electric field behaves very uniformly. We're within a millimeter of this sheet of charge, so it's a good approximation. We can say it's a uniform electric field. It's equal to the change in voltage over the change in displacement. The change in voltage is 1.59 volts. The change in displacement in standard units is equal to the difference between 0.000725 meters and 0.000515 meters. We plug in the numbers, and this tells us that the electric field strength has to be 7,571 volts per meter. Now we know E, we're looking for Q, the total charge. We have that E was equal to Q over epsilon naught A, so with a little bit of algebra, we can say that Q is equal to epsilon naught times E times A. Epsilon naught is a constant, 8.854 times 10 to the negative 12. E we just found to be 7,571 volts per meter, and then capital A is the area, and we have the dimensions. 0.172 meters by 0.155 meters. So we just multiply everything together. We get 1.79 times 10 to the negative 9 coulombs. And if this were a test question, probably the correct answer would be written as 1.79 nanocoulombs. Perfectly ordinary amount of charge. I want to move on to discussing materials. And even insulators can have some electrical properties. I can't get charges to cross through an insulator, but there are some insulators that do respond when there is an external electric field applied to them. And these materials are called dielectrics. What's a dielectric? Why is it so important? Well, let's consider the fact that there is such a thing as too much charge on a capacitor. I can't allow charges to build up infinitely on a capacitor. What happens is I'll reach an electric field strength so strong that charges will spontaneously cross the gap from one plate to another plate. The voltage difference, the electric field is so strong, it creates such a strong force that it's forcing charges to move across the gap from one plate to another. there's a limit, and that limit, if I have just air or vacuum in between the plates, is 3 million volts per meter. If the electric field exceeds 3 million volts per meter, then we're going to start getting sparking effects. Charges are trying to move from one plate to the other plate, and that defeats the purpose of the capacitor. We might want to store larger voltages or larger charges, at least, on these capacitors. And these materials called dielectrics help us. Not all insulating materials are dielectrics, but all dielectrics are insulating materials because charges can't travel through them. However, they do allow for us to modify the properties of a capacitor and allow for this greater charge buildup on a capacitor. In addition, the dielectric is simply a block of material that I could put between the plates. And so as you see in the figure, there's the additional advantage that dielectrics provide structural support. To understand how to quantitatively apply the effects of a dielectric, we need to define a new quantity called the dielectric constant. The dielectric constant is denoted by the lowercase Greek letter kappa. That's that script-looking lowercase k you see on the right-hand side. But it's really a lowercase Greek letter kappa. And it is a unitless quantity. Does not have units. It's simply a multiplicative factor. And the dielectric constant is going to affect the capacitance of a substance. The capacitance of a substance, of a device, the capacitance of a device changes if I insert this dielectric material in between the plates. This dielectric material has a specific dielectric constant. Let me show you a little bit by what I mean about that. If we go to the page in the textbook that discusses dielectric constants, you'll see table 19.1 in the textbook, dielectric constants and dielectric strengths for various materials. The dielectric constant is a unitless quantity. You can see that vacuum has a dielectric constant of 1, and air has a dielectric constant of barely more than 1. But there are plenty of materials, neoprene, nylon, polystyrene, silicone oil, Teflon, even water, that have dielectric constants other than 1. Notice that all of these dielectric constants are greater than 1. Vacuum has the smallest dielectric constant exactly equal to 1. The dielectric strength is a measure of the maximum electric field that I can have across this dielectric material. Now, there isn't necessarily a strong relationship between the value of a dielectric constant of a material and the dielectric strength of a material. So, for instance, we can take a look at this substance, strontium titanate, and it has a dielectric constant of 233 and a dielectric strength of 8 million. Whereas bakelite has a dielectric constant of only 4.9 and a dielectric strength of 24 million. So there's no relationship you need to worry about regarding the dielectric constant and the dielectric strength, but know the difference between them. The dielectric constant will allow us to change the value of the capacitance of a device by the presence of the material, and the dielectric strength tells us the maximum electric field that we can have in between the plates. What does a dielectric do? If I have two equal but oppositely charged plates, and you can see on the left-hand side I have a positively charged plate, and on the right-hand side I have a negatively charged plate. In between these plates I place my dielectric material. Now, the dielectric material is made up of atoms or molecules. And atoms and molecules, even at the individual atomic scale, can have electrical properties. And so, for instance, one side of an atom or molecule can tend to have a positive electric charge, and the other side have a negative electric charge, rather than have the charge be uniform throughout the entire volume. There can be an asymmetry in the distribution of charges. If this is the case, and if these molecules are allowed to pivot around, when I place this dielectric material in between these equal but oppositely charged plates, the negative side of the molecule is attracted to the positively charged plate, and the positive side of the molecule is attracted to the negatively charged plate. Without the parallel plates, with no electric field, the orientations of these molecules represented by the ovals would be random. One side would be negative, the other side would be positive, but they would be pointing in all sorts of different directions. But I place them between these equal but oppositely charged plates, and these atoms and molecules can rotate themselves around to align with the external electric field applied by these plates. And notice that each of these little atoms or molecules, they have an electric field that runs from the positive charge to the negative charge. Each of them has a tiny electric field that runs in a direction opposite to the external field of the plates. Therefore, the net electric field between the plates gets less when I insert these dielectric materials in between. So there is a weaker electric field between the plates, leading to a weaker electric force, making it less likely for these charges to spark, to try and go from one side to the other side. So I can place the same amount of charge on the plates, but now I have less chance of this plate's electrical integrity being compromised through sparking. And in addition, we have this material in between the plates providing structural support. So it's a win-win situation. So you might see each of these macroscopic electric field lines from the parallel plates and all of these little microscopic electric field lines from the individual atoms and molecules. You just get that the net electric field is less than just the electric field provided by the plates. Therefore, same amount of charge on the plates leads to a weaker electric field between the plates and leads to a smaller voltage difference across the plates, and it allows you to store more charge more safely. But what would happen if I had a parallel plate capacitor with no dielectric in between it, and an otherwise identical parallel plate capacitor with a dielectric in between it, and I charge them both up to the same voltage? What's interesting is that because of the weaker electric field with the dielectric, if I want to have the same voltage across the plates with the dielectric in between, I have to have more charge. So for the same voltage, a plate without a dielectric will have less charge than a plate with the dielectric. Now think about that, and imagine this situation right here. I have a parallel plate capacitor, but we only have half of the volume in between the plates filled with a dielectric. And I want to place charges on the plates. And we place these charges on the plates. What do you think is going to be true about the electric field between the plates? Will it be less? Will the electric field be weaker in the realm of the dielectric material? Will it be stronger in the realm of the dielectric material? Will it be the same in the realm of the dielectric material? Or, and this is kind of a nonsense answer I made up, will the charges be oscillating back and forth such that the electric field is stronger in the dielectric, and then later weaker, and then stronger. This last one is nonsense, because the assumption is that we have a static situation. The charges are not moving. If the charges are not moving, then the electric field is going to be constant. Now, it might not be uniform. We might have a weaker electric field in the dielectric. We might have a stronger electric field in the dielectric. And that's for you to figure out. The purpose of a capacitor, or one of the purposes anyhow, is to store energy, to temporarily store energy in the form of electricity to be released later. So I want to discuss a little bit about energy in an electric field, because the field itself, if there's a region in which there is an electric field, there is energy in that region due to the presence of the field itself. So wherever there's a volume in which there's electric field lines, there's energy in that region. And I want to discuss how much energy is there. We're going to start by imagining the energy in a parallel plate capacitor. And we have a formula for the energy in a parallel plate capacitor: 1/2 times the capacitance times the square of the voltage. If we have a dielectric, then that capacitance is equal to kappa times epsilon naught times A over D. And so I can say 1/2 kappa epsilon naught A over D times the square of the voltage. We're also going to take advantage of the fact that between the plates of the capacitor, the electric field E is uniform. And the electric field for a uniform situation is voltage over distance. So in this case, the distance is simply the gap from one plate to the other plate, which is little d. And so the voltage difference from one plate to the next plate is the electric field strength E times little d. And this subsequently allows us to say that the potential energy, the electric potential energy, is 1/2 times kappa times epsilon naught times A times D times E squared. And A, the cross-sectional area, the area of a plate, times the thickness D, that's the volume of the capacitor. And so the electric potential energy is 1/2 times kappa times epsilon naught times the volume times E squared. And what we're going to do is we're going to divide both sides by the volume, capital V, and we're going to define a new quantity. Energy over volume, we are going to call energy density. Energy density is comparable with density as you know and love it. You're used to saying density equals mass over volume. And that's true, but now we're going to have to say that's mass density, so that we start distinguishing with other kinds of density. I can look at energy per volume, and that's energy density. And we're going to denote energy density with a lowercase letter u. And in this circumstance, because we're talking about an electric field, we're going to say little u subscript e. And based on our hand-waving argument, we get that it is equal to 1/2 times kappa times epsilon naught times E squared. And what this means is that the energy in a volume, the electrical energy in a volume, is proportional to the square of the electric field. I want you to keep this in mind, because this is going to be important when we discuss the nature of light and how light is an electromagnetic wave. And one of the things that we'll be looking at is the energy density and how the energy is proportional to the square of the field strength. So file this as something that becomes very important later, but we can also look at an example with it now. We can ask the question, what is the average electric field strength if we have a sphere made of neoprene and the radius of the sphere is 4.57 centimeters, and we're told that the total energy in the sphere, the electrical energy, is 61.3 millijoules. Well, we have this relationship between electric field strength and electrical energy, and our intermediate value is energy density. So what I want to do is I want to calculate energy density. Energy density is total energy divided by total volume. So I need the total volume of a sphere. And the total volume of a sphere, the formula is 4/3 pi r cubed. R in standard units is 0.0457 meters. And when I plug that into the expression for the volume of a sphere, I get 0.0003998 cubic meters. I have the volume. I can now find the energy density. The energy density is the total energy divided by the volume. In standard units, the total energy is 0.0613 joules, and we just calculated the volume as 0.0003998 cubic meters. And so the energy density, when I divide, I get 153.3 joules per cubic meter. So I have one side of the equation on the previous slide, little u subscript e. On the right-hand side, I have 1/2 times kappa times epsilon naught times e squared. I'm trying to find e, and epsilon naught is a constant. But kappa, that's the dielectric constant, and I have this material neoprene. So I'm going to look up the dielectric constant of neoprene, and neoprene has a dielectric constant of 6.7, unitless quantity, mind you. So we have the dielectric constant of neoprene. Let's use it for kappa. And we want to solve for E, so first I'm going to solve for E squared. E squared is equal to 2 times the energy density divided by kappa times epsilon naught. The energy density is 153.3 in standard units. Kappa is 6.7. Epsilon naught is 8.854 times 10 to the negative 12. I get that E squared equals 5.169 times 10 to the 12. And I take the square root. And I get that the electric field strength is 2.27 times 10 to the 6 newtons per coulomb, which frankly is a perfectly ordinary value for an electric field strength. That's it for this. We'll see you in class. Bye-bye.